Okay, so on our final stretch here, phase shift. So if we draw, let's give ourselves three axes here. Now I'm going to draw the first and third picture here. I'm going to talk about phase and in phase, or out of phase, sorry. So here's a sine wave, and what I'm going to do is I'm going to draw completely out of phase. So completely out of phase would look like that. Excuse me. And the reason it's completely out of phase is because where there was a crest, there's now a trough. Where there was a trough, there's now a crest. Well, kind of. Oops. Quit drawing lines. There we go. So close enough. So in between, we call this completely out of phase. Well, there's going to be a partial out of phase as well. So you end up with something that looks like this, where the actual crest or trough occurs in the middle here. So as it oscillates, you're going to get a wave like that. So this is what we would call out of phase. And this is either half or partial out of phase. All right. Which brings me to some constructive and destructive interference. Constructive / destructive interference. So just a quick run through on that again. Okay, it hasn't changed. Very, very important though when we start getting into our slit experiments, single slit and double slit experiments. So if I have two waves approaching each other, both on the same side, when they collide, they create what we call a supercrest or super trough. So if we have that amplification with sound, it becomes our loudest point. Okay, so if we have two crests meet each other, we end up with what we call a supercrest, which makes things very, very loud. In terms of light, it becomes very bright. All right, if something becomes very, very bright, and we can prove light, and this is another, maybe if I remember to bring in, or you can ask me, bring in the flashlights. We turn out the lights and we turn flashlights on. What you'll find is the regions that overlap, or the region that overlaps, right in here will be more bright or brighter than the outlying regions. So where those flashlights overlap, you end up with an area of brightness. Okay. Destructive interference then down below. We have a crest, a trough. We end up with a nodal point. All right, so the waves cancel out or destroy each other, I guess you'd say. Well, destroy is not really the right word because they do continue on afterwards. So, all right, so there is your quick review. And what we're really focused on is kind of this principle here. And we're going to talk about it when we get into Young's experiments, talking about regions of brightness and regions of darkness. And it's going to be because of that constructive and destructive interference. Okay, a couple of quick sort of conceptual things I want you to know about. Talk about rectilinear propagation, and that is simply saying light travels in straight lines. In straight lines. And that's all that is saying. So, what do I have set up here? I've got a screen set up, and what I want to do is, my end view is not in the right location. It is side view. So here is my side view. Actually, the side view is fine. That's all right where it's located. It's the end view that's shifted on me. It's not a big deal. Okay, so if I have a point source, all right, so if I have a point source, I'm going to use blue light here, then the light rays are going to put an object in front. Those light rays are going to travel like this and like this. And what will happen with the point source is that we're going to have this region right here creating a black box, assuming that that original, the shape I put out front, was in fact a square. All right, so that's for a point source. But for people that think about it and have noticed their shadows before, some parts of your shadow are darker than the others. So what happens if we don't have a point source per se? So what happens if we have a larger light source? Well, my light rays are going to go here and here. The bottom is going to go up there and here. So if you take those light rays emanating out in all directions from every point, what happens is you get a region where there is no light, and we get regions where there are some light. All right, so what does that mean? Well, the resulting shape looks like this and like this. So in here, there's no light reached it. And outside, some light reached it. So I'm not going to color it in. And what we have, what we call these total blackout areas where there is no light at all. We call that the umbra. And the regions where some light is getting there, but not all, we call it the penumbra. Okay, so they're not quite as dark. So because some of the light is getting through. Okay, some of the light is getting there, just not all of it. So it's not enough light to light it up like the rest of the wall, but it's definitely not a dark region where no light's reaching whatsoever. All right. Quick look at the pinhole camera and how it works. So basically the pinhole camera is placed in a box. So I need to finish off the box. There we go. At the back of the box, we put some film, and that's where my image is created. So what happens, they open the hole. It takes a very, very, very long time, but the top of the light source will go down there. Bottom of the light source will go over there. So it goes and enters that small hole. So there's the pinhole, so to speak. The measurements then, here we have the height of the object. Here we have the distance of the object away from the screen, so DO. This would be the distance of the image from the box. And then there is the height of the image. So what you see is we have similar triangles. Going way back to grade 10, similar triangles. So that means there is a proportional relationship, and we find that the height of the image divided by height of object is equal to distance of image with respect to distance of object. So that is our formula for the pinhole camera. If you want to know more about it, definitely go ahead and Google the pinhole camera, but it's one of the earliest types of cameras that existed. You used to have to sit for very, very long periods of time because the film wasn't nearly as sensitive, and you had to wait for that image to kind of burn into the film or set into the film. So those are your first types of camera. Okay, so reflection. Types of rays here. Just one sec. There we go, all fixed up. This is just terminology that we need to be aware of when it comes to doing some of the questions and experiments throughout the unit. Parallel rays. So if we have parallel light rays, that means the light rays don't cross. They are all in the same direction. The only source that will generate parallel rays would be a laser. Okay. Diverging rays. They would extend out and never ever cross, but they would meet at one common point. So that would be similar to our point source, a light bulb, for example. And finally, converging. So that means if you see the word converging, that means the light rays are coming and approaching a particular point. So it's kind of like several spotlights aimed at a target. All right. So we got our parallel, we got our diverging, and we have our converging. Incident versus reflected ray. Again, just reviewing. So that light ray strikes the surface, say a mirror, shiny object, something that's distracted Luke, for example, and that angle is measured from the vertical center line. So there is our angle of incidence. That is our angle of reflection. It's the reflected ray. All right. So that is our incident versus reflected ray. All right, so moving into plane mirrors, images in plane mirrors. So that's when we're looking straight on. So if we were to look at a plane mirror, call that my mirror, and I draw my super cool eye, that would mean that if I look in the mirror, it looks like my eye is looking back at me on the other side, and the distance would appear to be the same. So the distance from here would be equal to my distance here. So those two lines would be of equal length. All right, so we have our original, and we have our image. And we would find that when we look in the plane mirror, our writing and hands are inverted. So your left hand appears to be your right hand in the mirror, and so on and so forth. What happens if we look at a plane mirror at an angle? So my eye appears down here. If I'm looking at a person, for example, standing right here, I would see the person same distance into the mirror. So this distance and this distance would be the same. But my line of sight is along there. So the reason I see them over there is because my reflected ray to the actual person follows the angle of incidence and reflection. So right here, I'd have theta I, and here I'd have theta R, and theta I equals theta R. So there is our geometry as to why we see people where we do in the plane mirrors. It's simply that angle of incidence, angle of reflection, but the appearance follows that red line behind the mirror. All right. And I'm going to have to extend it into one final video here just to cover the last little segment. And then, like I said, during this time, probably doing some labs here because not a whole lot of homework associated with this section.